Hello there, this is Craig Hain. My students call me Dr. Dell, and I have written a book recently called Golden Rule Math for STEM math students. And this is really aimed at any students or teachers or anyone else that's interested in STEM and what is the math they need for it. And I call it the Golden Rule Math book because this is the way I would want to be taught STEM math today, knowing what I know with modern 21st century technologies. And this video is all about that and what you can do to achieve that. Now, in order to do that, I want to share the screen with you. And this is all about now well, first of all, this is my homepage, craighane.com. And you can go here and learn all about me. So you wonder, who is this guy? Well, you can go there and learn about me. And we're starting a new STEM math club, which we believe will help schools and then the students and the teachers really get up to date in modern technology. Now, you can go get this book at Amazon, either Kindle or paperback, $3 or $10. And I will also tell you then later how you can, when you join the club, you can get a free PDF copy of it. This is the table of contents of this book. And it has a lot of things in it you need to know. This describes really the math you need for STEM math today in great detail, and a 6-tier program that I've developed that's unlike anything that's out there today. And you'll learn why I'm going to tell you about on this video and how it all came about, because this video is essentially about chapter 10, which is the full math story of STEM. This is the full story. And now I am not going to read this chapter verbatim. I am going to sort of go over it in a very quick form, and you just need to probably listen, not try to read, because I'm not reading it verbatim at all. But it's what you need to know if you are interested in STEM, either as a student or as a teacher or whatever your reason might be. So now you can get this book and just read this. It's a 16-page chapter, and I think it covers it in great depth. And it's really aimed at anybody interested in STEM. Now, if you don't know much about math, this will be a pretty technical thing. I'm not teaching math, but I'm talking about math education. Then you'll just sort of want to listen to it and sort of get an idea of it and see what it's about. If you do know math or science, or if you know someone that does, then this chapter would be very good for them. First of all, I want to tell you this. There are 2 approaches to learning math and teaching it. One is called heuristic and one is called rigorous. Now, it's very interesting. A heuristic approach is where you approach it practically, and you try to understand concepts and tools in a very practical way so that it makes sense and it's logical, but it's not rigorous. Rigorous means you're trying to prove some theorem or statement from a set of axioms, and that's much harder to do. That's something mathematicians really want to do, but scientists and engineers aren't so interested in that. They really want to know what's the concept and what's the tool. And that is the way our ancestors actually approached math for a long time. Now, the exception to that was Euclid, who wrote the Elements of Geometry, and he was rigorous. And it's very interesting, very difficult to understand that book. There's a lot of proofs, and some students like it. I happen to kind of like it when I was young, but a lot of students don't. And a good example of that is a Pythagorean theorem, which you've all heard about. Now, there are many proofs of it, and some are heuristic, and they're very easy to understand, and they really make you understand it. Euclid did a rigorous approach. It was proposition 47 in book 1, based on what's called the windmill diagram, and it's very difficult to follow. And so that's the difference between rigor and being heuristic. And I'll tell you another story about that in a moment that's very, very important. Now, one of the things that I will tell you about in modern STEM math, I mentioned in this, is there's a great book called Pre-Calculus Mathematics in a Nutshell, written by George Simmons, Dr. George Simmons. He was the greatest math teacher of the 20th century, in my judgment, because he wrote the greatest book on differential equations I've ever seen, the greatest book on calculus I've ever seen. And he also wrote the best book on topology and modern analysis, which is the math theory you need for things like quantum theory. That's how I got to know him. I was teaching advanced theoretical math at several schools, and most recently Rose-Hulman Institute of Technology in Indiana. And this was the book I used, and that's how I got to know him. But he came out in 1988, he came out with this wonderful book here. And you can go buy it on Amazon for less than $20, and anybody that's interested in STEM math should buy that book. I use that one book in my 6-tier program. Now, here's the things you got to know if you're going to study STEM, and I covered it very briefly. First, the number system. You got to know what are called the real numbers, and if you know any math at all, that corresponds to points on a straight line. You put a 0 and a 1, makes a ruler out of it, and then every point is assigned to a real number and vice versa. They call that real numbers. And you can understand them as decimal expansions. If you use the base 10, which most of us do, then any number you can expand in a decimal expansion is a real number. Now, there are something called hyperreal numbers you've probably never heard of, and I'm going to tell you about them a little bit later in this video, but it's extremely important for STEM today when you're learning STEM math and applying it. And then there's something called complex numbers that you probably have heard of if you know anything about STEM math. And this is where the numbers correspond to points in the plane. Real numbers are a straight line, complex numbers points in the plane. It took our ancestors literally centuries to develop these number systems. And in fact, the hyperreal numbers were not developed, as you'll learn a little bit later, until the 20th century. In fact, in 1966 is when these were developed. Now, you need to understand these heuristically. Heuristically, you need to understand them if you're interested in science and engineering. If you're going to be a theoretical mathematician, you'll have to learn it rigorously, but that should come later. First, you should learn it heuristically. Then you can later learn it rigorously if you want to. Now, just for example, in the real numbers, I said they're decimal expansions. Well, if they're repeating decimal expansions, those are called rational numbers. They can be expressed as the quotient of two integers. But if they're a non-repeating decimal, they're called irrational numbers, which means they can't be expressed as a rational number. They're not rational. That's why I call them irrational. That was the name they gave them. And this, by the way, really upset mathematicians tremendously. In fact, the Pythagoreans really discovered irrational numbers and retreated from numbers because of it. And there's subsets of them, algebraic and transcendental subsets of the irrational. Now, theoretical mathematicians care about this. Applied mathematicians, scientists, and engineers don't care about this at all. So this is not something we should be teaching in the beginning. We should only be teaching this to people that want to become theoretical mathematicians, not scientists and engineers. Complex numbers, I just said, correspond to points in the plane. That's very important. It's critically important. In fact, you cannot do modern science without understanding them. Now, they're easy to understand, it turns out, because they involve what are called trigonometric functions, which we'll talk about a little bit, and infinite series. And if you understand that, then you'll understand complex numbers. In fact, there's a complex number equation called Euler's equation that Richard Feynman, the great physicist who was responsible for modern approach to quantum electrodynamics, he said that was the most important equation in mathematics. And for him, it was, because without that, you can't understand complex numbers really. And without complex numbers, you can't do quantum theory. And so this is extremely important. And the good news is it's easy to understand, very easy. I teach it in tier 4 in my 6-tier program, and it's easy to understand, 11 lessons and it got it. And that's the key, by the way, that Euler equation is the key to it. And I might add, that's not taught in high school very often. Now, hyperreal numbers are important because they include something called infinitesimal numbers. Now, our ancestors started using infinitesimal numbers way back thousands of years, a couple thousand years ago. I'll tell you a little story about that in a moment. Unfortunately, when they started in the 1800s, developing numbers rigorously, they couldn't figure out how to create an axiomatic system that had infinitesimal numbers in it. And so they banned them at that point. And I'll tell you a little more about that in a moment. In fact, they figured out how to do it in 1966. Abraham Robinson did. Okay, now let me tell you the story about this that involves rigor versus heuristic. Euclid, the great Euclid, with his geometry, proving theorems rigorously, defined the area of he defined a number called pi to be the ratio of the circumference of a circle divided by the diameter of a circle. And he proved that this ratio was the same no matter how big the circle was. C divided by D was always the same number. He proved that, and they call it pi. So pi is C divided by 2r. You've probably seen this. C equals 2 pi r for circumference of a circle. Euclid knew that. He proved it. What Euclid could not do is figure out a formula for the area of a circle. Couldn't do it because everything he did was rigorous and he couldn't do it rigorously. Well, then a couple hundred years later, what many people think is the greatest mathematician of antiquity, a guy named Archimedes. I'm sure you've heard of him. He used a heuristic approach using something kind of like infinitesimals to prove that if you took the diameter of a circle and divided by 2 and the circumference of that circle divided by 2, and if you multiplied them, guess what? That's the area. And he proved it heuristically. Amazing. Just a couple hundred years after Euclid. Now, he couldn't prove it by modern standards rigorously, but it was heuristically proven, and that's what people have used ever since. And if you use a little algebra, then that becomes the area is pi r squared. You've heard of pi r squared, I'm sure, if you know any math, any geometry at all. Well, Archimedes was the first one to, quote, heuristically prove it. And Euclid hadn't done it, like I said. Now, Archimedes did something even more significant. He took a sphere, a ball, and the question is, how can you, if you know the radius of the sphere, how can you calculate its area? Or how can you calculate its volume? Very important. And Euclid didn't even attempt that. He couldn't even do the area of a circle, let alone that. Well, Archimedes was able to say, if you took this sphere and inscribed it in a cylinder, so it fit just perfectly in it, it's easy to calculate the area of a cylinder and the volume of a cylinder. That's easy. The sphere, what's that? Well, he proved it's 2/3 of that. Amazing. And he used a heuristic proof using something kind of like infinitesimals to do that. In fact, he considered that his greatest achievement, and he wanted that on his tombstone. That was his greatest achievement. And that was the most amazing things that probably Archimedes did. Now, when I teach math in my 6 tiers, in tier 2, I teach that heuristically. I show what Archimedes did. And of course, it wasn't in Euclid's Elements. Now, let's move up into the more modern times. In the 1600s, that is when mathematicians began to really get deeper into math and extend it, and they developed something called calculus. Now, if you know what calculus is, you know what I'm talking about. If you don't, it was a modern STEM math subject. And in England, Isaac Newton discovered it. And on the continent, European, I think in Germany, Gottfried Leibniz discovered it independently. And Newton used it to create Newtonian physics, which was the beginning, really, of modern science. Well, Galileo started it with some observations he made, but Newton was the first one to mathematically, heuristically develop what became then Newtonian physics, the laws of motion and all of that. And then you could predict pretty much the orbits of planets, and he verified Kepler's laws and all that, if you know the history of science. But Newton's approach to calculus was kind of hard to understand. He used something called Fluxions and fluents and so on. Leibniz used infinitesimals, and he did it in a way that was, I think, much easier to understand. And he had disciples, the Bernoullis, and then Euler was his most famous one in the 1700s. And between Leibniz and the Bernoullis and Euler, they used infinitesimals, and they created calculus, as is taught today, really, as we understand it today. And then from calculus, you go to differential equations. And I'll talk about that in a little bit further on in this video that's in this story. These are the workhorses of modern STEM, by the way. And so this was all done in the 16 and 1700s. Now, in the process of doing that, they created a lot of manual tools. And I'll talk about that in a moment. But here's something that happened that's really kind of amazing. And by the way, if you go back and read the works of Leibniz, in particular of Euler in particular, he was the most prolific mathematician of all time in the 1700s. His proofs are wonderful, but they use infinitesimals. Well, in the 1800s, mathematicians decided to make all mathematics rigorous, like Euclid had done. And so they were creating axiomatic systems and proving theorems. And they succeeded in doing that first for the integers. And then first the natural numbers with the Peano axioms. And by the way, you learn all about the natural number system and how to use it practically without studying the Peano axiomatic system, I'm guessing. And then they went to integers and rational numbers, and then real numbers. They did it all axiomatically. And they actually did complex numbers too. But when they got to the concept of infinitesimals, it didn't fit in any of their systems. And they couldn't create an axiomatic system that they fit in. So in the mid 1800s, mathematicians said, well, since we can't create an axiomatic system that has infinitesimals in it, we banned them. Now, that was a horrible thing they did because they're so useful heuristically. And that's how engineers and scientists understood calculus. And that created in the mid-1800s a bifurcation in STEM mathematics. The infinitesimal numbers make understanding calculus much easier. And I use them when I teach calculus in my 6 tiers. Applied mathematicians and scientists at that time went their own way. They continued using them right all the way through. But unfortunately, the theoretical mathematicians got to write and influence math educators to write our calculus books, so they went rigorous. They used what are called limit theorems, epsilon delta proofs, which are very difficult. So there was no more infinitesimals in our calculus books. I consider that was a horrible setback for math education. It made calculus much harder to learn. Well, guess what? In 1966, a great mathematician named Abraham Robinson, he figured out how an axiomatic system that had infinitesimals in it. They were called the hyperreal numbers, very rigorous now. And that had to be the year I got my PhD in algebraic number theory. And I was studying theoretical math, and I saw this happen. Oh my golly, that's wonderful. Now we can put infinitesimals back into STEM math. That makes it much easier to teach. Well, guess what? I was wrong. That didn't happen. I thought it would. Jerome Kiesler from the University of Wisconsin actually wrote a calculus book with infinitesimals, and no one would adopt it. It's out of print. I knew Jerome. I felt sorry for him. He wrote a great book. No one adopted it. Well, our calculus books, this is 2021. I'm doing this video for the future STEM math club members, and they still haven't caught up yet. At least none I know of. If you know of one, let me know. And, you wonder, what could that be? Well, the only thing I know is we have a huge investment in the current calculus books, the way it's taught. And by the way, infinitesimals are just one problem. There's actually a much better story. It gets much better than that. In fact, the story for calculus and STEM math really gets really hugely better in 2019. I'm sorry, 2009. And the plot really thickened. But before I get into that and tell you what happened in 2009 that just revolutionized modern STEM math education, and believe me, it revolutionized it, let me tell you what's involved in STEM. Now, if you know math and you know STEM, you'll know this, a little review. If you don't, just listen to the words. There's something they call functions. Very simple to understand. Functions easy to conceptually understand. And they have different kinds of functions. They have polynomial functions. They have trigonometric functions. They have exponential functions. Then they have their inverses. For example, the logarithm is the inverse of exponential. And they have composites of these functions. And these are wonderful functions that our ancestors developed over many centuries. Then they have something they call infinite series. And these are like infinite polynomials. Now, Newton used these a lot, by the way, and our ancestors used them. They weren't rigorous then. We've made them rigorous since then. But these guys, when they did it heuristically, had a very good sense of what was right and wrong. Once in a while, they'd make a mistake, but usually not. And these are wonderful. So these are really the creations of math that you use for models. Now, in order to analyze functions in infinite series and these things, they had to create tools to do it, tools to analyze them, and then to solve problems that would come up, like differential equations, for example. Well, these math tools were manual. All they had was pencil and paper or chalkboard or whatever. They didn't have any modern tools like computers or anything, nothing like that. So they invented these manual tools, and they were wonderful manual tools. Think of carpentry. Go to a museum and look at the manual tools that they developed for carpentry back in the 17 and 1800s. Wonderful, but hard to use, difficult to master, hard to use, and limited in what they could do. But that's what they did. Now, if you take a function, which is, like I say, that's really the building block of all modern math models and science, you want to graph it. That means you want to lay it out. You want to see what it looks like for all the different values in the domain. So you make a graph that lets you a picture of the function. You can understand a picture of a function a lot better than just looking at the formula or the definition. The picture is everything. Well, back in those years, you had to graph it point by point by point manually. Very, very difficult. And you want to know things like, what's the maximum? What's the minimum? When's it concave up, down, points of inflection? Well, calculus is what let us do that much easier. we can now graph a function and identify maximum, minimum, points of inflections. And then you want to know the area under a function, extremely important. What's the area under the graph? Here's the function curving around. What's the area? That was called integral calculus, and that was based on what's called the fundamental theorem of calculus, arguably the most important theorem in the history of mathematics, because modern science was all based on it. That's what Newton discovered. That's what Leibniz discovered. Extremely important, fundamental theorem of calculus. And then the manual tools. Now, I'm not going to teach you math here, so if you know that, fine and dandy. If you don't, you'll learn. Now then, they had something they call differential equations. Now, if you have an algebraic equation, you know some math, the solutions are numbers. If you have a differential equation, the solution is a function. Well, it turns out differential equations are what you set up as a model for some science or engineering thing. You have to solve the differential equation, get a function. Then you use calculus to analyze a function. This is STEM math. If you're going to study STEM math, then this is what you have to learn. There's no, as the old saying goes, short road to glory. You got to learn these things. Now, the problem is the way they've been taught historically by our ancestors is difficult, extremely difficult. But math is the foundation of all STEM subjects, science and engineering and technology. It's a universal language. I call it God's language. You can speak English or Chinese or Spanish or German or whatever. Those are natural languages, and we all have to speak some natural language to communicate. But if I speak English and then I'm talking to a Chinese that doesn't know English and I don't know Mandarin, we don't communicate. But math is universal. 2 + 2 = 4, the natural number system anywhere. Okay. Now, here's a fundamental problem we have today with our standard math curriculum being taught in virtually all of our schools and all of our textbooks, what our teachers are trained to teach, whether it's a public school or a private school or a home school or whatever. It's called the standard math curriculum. And here's the problem. I've been talking about these manual tools. They were wonderful by our ancestors in their day, but they're very difficult to learn and master and use. And so you spend most of your time with students trying to teach them how to master these manual tools and use them. And that's the big math barrier. That is very, very difficult. And particularly some of the manual tools are very difficult to learn. I'll tell you which ones in a moment that flunked more kids out of engineering school that I know of than anything else. And they're difficult. And that's just for everybody. They were tough for me. I mean, it takes a very persistent person to really put up with all you got to do to learn those things. I mean, I don't know what to compare it to doing carpentry with manual tools from the 18th century. Just think how hard it would be to become a good carpenter. Not very many people did they? These manual tools are time consuming. They're error prone. They're very hard to master. Just keep that in mind. And that's what we're teaching today, by and large. We made it a little bit easier with calculators and graphing calculators, but not much easier. And you're going to learn about that in a moment. And that applies to everything. Now, they did come up with a manual tool that was better than just multiplying and dividing with those tools. They call logarithms. These are the inverse of exponential function. A couple hundred years ago, they invented logarithms, and those make it easier to do multiplication and exponential and division and stuff. And then they were able to put those onto a manual tool called a slide rule. We used to call it a slipstick. And that's really basically log tables. If it's a round slide rule, not only do they have that, they have trig tables on it, because they developed logarithm tables and trigonometry tables, and you had to master them to do science and engineering. I taught in engineering school back in the early 70s, and we had to teach them how to use logarithms, log tables, trig tables, just to solve the arithmetic, just arithmetic. And I mentioned calculus was invented in the 1600s. It's used to analyze functions. The manual tools were developed by Leibniz and Euler and others. Wonderful tools, hard to master. And then we had to solve the differential equation, and that was even harder, and so on. Okay, so that's what happened. Now, if you want to become a STEM professional, up until 2009, that's what you had to do. You got to learn the manual tools. Concepts, by the way, are easy to learn. It's very easy to teach concepts. I have free videos on my website you can go look at, and I got like 3 videos to teach you the concepts of calculus. Anybody can understand the concepts of calculus. Tools are another thing. Well, now in the 21st century, in fact, in 2009 to be exact, this all changed. And unfortunately, our educational system hasn't caught up with it yet, our math education. So like I said, the problem we have with math education, even today, is the manual tools are a barrier and a challenge. Not the concepts, it's the tools. Now, why am I telling you this? Well, as I already said, our current programs are still teaching manual tools. In fact, I will tell you this. Integral calculus, which is how you use the fundamental theorem to get area under a curve, in my opinion, flunked out more kids from engineering school than anything else. It was a great barrier. And the reason was they had something called techniques of integration where they had to find what are called antiderivatives. And that can be very difficult to do, sometimes impossible. And when you're first studying math, going through it, it's very challenging. Now, the teachers that have taught it for several years get pretty good at it if you do it over and over and over. So for the teachers, it wasn't too hard, but for the students, it was very difficult. And in fact, it was difficult for the science teachers and the technology teachers and the engineering teachers. They'd often come to the math teacher and say, I've got this problem. How do I do this? Excuse me. There were also tables of antiderivatives, books that had antiderivatives. So you go, maybe you could find it in a book, or maybe you could apply a technique. Very difficult. Well, two miracles actually happened, and I want to tell you about the first one first, and then the big one come a little bit later. First of all, doing arithmetic was difficult. Use a slide rule, right? And trig tables and log tables. Well, in 1972, Hewlett-Packard came out with the world's first scientific calculator called the HP35, Hewlett-Packard 35 keys. Wow. Log tables and trig tables are obsolete. Slide rules are obsolete. All a STEM professional had to do was use the calculator, and it was much quicker. I'm sorry about that. Well, anyway, this was a crisis for the math educators at that time because many of their books were obsolete in their courses. You no longer were teaching logarithms and trig tables and slide rules. You had the calculator. They didn't like it. Students were, I was around when this happened. The students were thrilled. They were buying a calculator and using it, and the math teachers were still trying to teach the old manual stuff. The students said, I don't want to learn that. I want to use a calculator. In fact, they wouldn't let them use it for a few years after it came out because it was expensive. And a lot of students couldn't afford it. Teachers couldn't afford it. Originally it was $2,500 in today's dollars. Then it came down half price in 2 years, and then it came further. And then Texas Instruments made one that was better, but they were expensive. The teachers were angry. They were depressed. Why? Well, they've been earning a good living teaching the old manual tools, and now they're going obsolete, and they know it. Many of the textbooks were obsolete that taught that stuff. I mean, I remember seeing that. It was quite a turmoil. I was teaching the advanced theory. It didn't affect me. And in fact, it didn't affect calculus and differential equations very much. And those are the workhorse of STEM. Those are the workhorse. So it didn't affect them very much. It made the arithmetic easier, but it still didn't make the manual tools for them easier. So STEM math didn't change that much. But in 2009, miracle number 2. Now, this is an earthquake. This is phenomenal. And this is what our education program hadn't caught up with yet. And this is why the STEM Math Club is going to be so valuable to both teachers and students. There was this great earthquake, made the first one minor. The first one was, maybe a 6 on the Richter. This is a 9. Well, let me tell you the story. And it's all about a tool that was introduced to the world in 2009 called Wolfram Alpha. Now, for you to really understand and appreciate how this came about and what Wolfram Alpha really is, I want to give you the history of it. So I'm going to back up to right after World War II. They started making what are called computers that you know about. And the first ones were made with vacuum tubes, much greater than any other calculating thing they'd ever had, but very difficult to use, very expensive. Then they came out with integrated circuits, with transistors, much better, much faster. Then they put transistors together, integrated circuits, even better. In fact, by the 70s, they were beginning to build computers with integrated circuits. And so they were much faster, much less expensive, still big and expensive. MIT, Massachusetts Institute of Technology, developed a sophisticated computer algebra program called Maxima. And what Maxima could do, I never used it, but it could solve calculus and differential equation problem numerically. I don't know all the details of it, but it could solve things that manually were very difficult. And now I could give you solutions, numerical solutions were pretty easy. Well, over in England, there was a guy named Stephen Wolfram, a young guy, a teenager. And somehow he got access to Maxima. I don't know how. There's no internet back then. I don't know what he did, but he got access to it. And he loved physics. So he started solving physics problems and publishing them. And to solve the problem, the equation, he would use Maxima. Things that he maybe couldn't, it was very difficult to do manually, but he could do it. Well, they were so impressed with this that he went to the greatest graduate school in physics in the world, Caltech, to get his PhD. And Richard Feynman was at Caltech. And Murray Gell-Mann, it was the greatest physics school in the country. Got his PhD, and guess what? Age 20 or 21, it was 1978, he got his PhD. And they were so impressed with him. I mean, theoretical physics, PhD, greatest school in the country, age 20. He won the MacArthur Genius Award, had money. Well, he said, I want to do physics, but I want a tool that's more powerful than Maxima. So, and he thought he knew a way to do it using symbolic programming. I don't understand it. But he went to work on it. He formed a company, in fact, to do it. And for technical reasons, that company failed. Then he formed another organization to do it. Ended up in Champaign, Illinois. And he did it. And in 1988, 10 years later, he introduced this thing to the world called Mathematica. Now, it's a programming language. And it was the most powerful programming language anyone ever dreamed of at that point in time, way beyond any other programming language, nothing to compare to it. And he knew Steve Jobs really well. And Steve Jobs had left Apple in 1985 and was developing something called the Next Computer, which was going to be a desktop computer, the more powerful than the Macintosh, which he had developed back at Apple. And then he got fired because they didn't want to promote it. That's another story. Well, the two Steves knew each other. In fact, Steve Jobs was the guy that gave Steve Wolfram the idea to even give it the name Mathematica, because they were debating on what to call it. Well, Steve Jobs said, call it Mathematica. And I don't know why, maybe because of Newton's book was Principia Mathematica. I don't know, but some reason. Well, anyway, when Jobs then came out with the Next Computer, they loaded it with Mathematica. It came with it. You know, that made the Next Computer now extremely powerful, because now it had this tool in it, Mathematica. And they bought 12 scientists and engineers all over the world bought them because they were so powerful. Students probably couldn't afford them. They weren't using them in schools because they were too expensive, but schools did. Well, over in Chern in Switzerland, they bought 12 of them. And Tim Berners-Lee, who worked there, used it on the side, the Next Computer and Mathematica, and he developed something that I'm sure you've heard of called the World Wide Web. Up until then, the internet was hard to use. I remember I was using it back in those years. I got my email address, craig@hain.com is my email address. I got it back before World Wide Web. And it's a long story, but I say it cost me $25,000. That's another story. Anyway, that doesn't matter. Anyway, that was the amazing thing. Now we're ready for miracle number 2. This is the biggie. Steve, by the way, Wolfram, once he developed Mathematica, he began to do more physics. And he spent about 10 years then doing physics from 92 to 2002. And he wrote a book called A New Kind of Science. And I met him when he was on a book tour at Indiana University. I'm from Indiana, and met him just, say hi to him and talk to him. In fact, I'm the only one I've ever met that read the book completely. Now, I'm sure a lot of people have, but I never could find anyone that had, because I wanted to talk to him about it. But anyway, then after that, he went back to they were developing Mathematica upgrade all the time, more and more and more. I think we're up to Mathematica 6.0 when this happened. About 2006, he got the idea, maybe there's a way we can create a program in Mathematica that'll be a tool where you can ask it a question and it'll just solve it for you. You don't have to, not write a program. Well, it turned out he could do that. In 2009, he introduced it called Wolfram Alpha. Now this, you may never heard of it, which is sad, because anybody that's studying 10 mathematics needs to know about Wolfram Alpha and know how to use it. It's phenomenal. He was able to do this. It's a very sophisticated Mathematica program. It runs on some big computer somewhere, I don't know, because when you go to Wolfram Alpha, which is free, you can ask it a question. And you got to know how to ask it right, but it's like driving a car. You got to know where all the buttons are and the switches and all that. But once you learn how to use it, it's like a powerful car, and compared to a horse and buggy, for example. And so and what I do in my training, you're going to learn in a minute, I teach you how to use Wolfram Alpha for STEM. Well, anyway, it's this very sophisticated program. Now, here's the deal. Here's what it'll do. You take any calculus problem, or pre-calculus for that matter, trigonometry and analytical geometry, but calculus and differential equations, any problem, and you give it to Wolfram Alpha, and bam, it solves it. Wow. If you've ever studied calculus, particularly integral calculus or differential equations, and you know how difficult those manual tools are, how difficult they are, you're going to say, oh no, that's amazing. I can't believe it. But it's true. It's absolutely true. And so what that does is that revolutionizes STEM math education. It revolutionizes it. There's just no other way to put it. The calculator sort of revolutionized it a little bit back in the 70s because it made arithmetic much easier to do. And that was wonderful. But this is much more revolutionary, much more revolutionary. Well, as you can tell from talking to me, I've been around a long time, and I've been teaching math for decades and decades. And I've known this problem that we've had with the math education system all my life. And there's nothing I could do about it. I mean, that's how you had to do it. It's like we lived in a horse and buggy era, and that's what we had. We had horse and buggies, and you had to learn them, and you had blah, 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 manual tools. Well, this came out in 2009, Wolfram Alpha, and I realized right away what it was. I said, oh my golly. Just like when the calculator came out in 1972, I told my fellow, I was teaching at an engineering school, and when the calculator came out, and one of the students had one. They were expensive, and I looked at it and go, oh my golly. I told my fellow faculty that now what we're teaching with slide rules and all that, well, now is obsolete. And of course they hated to hear that, but it was true. Well, anyway, this is what we are today. This now makes it obsolete. So I started in about 2011. Actually, I started playing with it in 2009. By 2011, I knew what it could really do. And I started developing a 6-tier program. And what I start doing, the first 3 tiers are still getting people ready for, first of all, the first 2 tiers are practical math. Just real, and you can learn practical algebra, trigonometry, and geometry. Practical algebra, geometry, and trigonometry in 1 semester using a calculator, which I teach all that. That's tier 1 and 2. Tier 3, I get you ready for the SAT, again with manual tools, because they don't let some Wolfram Alpha on SAT. Starting in tier 4, and I'll show you the syllabus in a moment, how that works. Then I start using Wolfram Alpha, and this just absolutely revolutionizes pre-calculus, and then of course calculus and differential equations. It's just unbelievable. And so then I go on and I use it through calculus and then differential equations. Today, you can take a student, it doesn't have to be a genius now, just a reasonably ambitious, reasonably bright student. I'm not a genius. I'm what I call just a reasonably bright guy that is willing to work, and I like it. And you start them when they're 12 years old, and by the time they're 16 or 17, they'll be all the way through differential equations. Why? With the new system, the new tool, you can learn calculus in 1 semester, and then you can learn differential equation in 1 semester. The concepts aren't hard. It's the manual tools, they're gone. I don't teach the manual tools. Well, actually, I do teach a few of the easy ones just for the heck of it, but you don't really need to. So the great math barrier of integral calculus and differential equations, this is the big barrier. Integral calculus and differential equations been eliminated. Talk to anybody that's been through, that's a scientist or an engineer or a medical doctor, because they had to take it for pre-med. Ask them what their experience was and their fellow student with integral calculus. See what they tell you. And with almost no exception, they're going to say, oh, that was really tough. That was really tough. And a lot of kids flunked it. And bright kids flunked it. It's just so much work. And it wasn't fun. Well, anyway, STEM math is no longer an impediment to learning science and engineering. And I said the analogy is like a modern automobile replacing a horse and buggy. The old technology with the manual tools, I just analogize it to horse and buggies. And Wolfram Alpha is like a modern automobile. If you had to take a 500-mile trip today, would you go in a horse and buggy, or would you go in an automobile? Well, obviously, you go in an automobile. Now, you have to learn to drive the automobile. If all you'd ever done was a horse and buggy, and you were an expert with horse and buggy, fine and dandy, but you still got to learn how to drive the automobile. And that's what I teach in tiers 4, 5, and 6, how to drive the automobile, how to use Wolfram Alpha. And it's easy to do, by the way. I mean, the students go through it real quick. Now, the sad thing is all high school textbooks, they're obsolete. Sorry, that's the way it is. And by the way, it's not the teacher's fault. Do not blame the teachers. They're not at fault for this. It's the standard math curriculum that's mandated by usually the states, and the high schools have to do what the states tell them to do. The public high schools. Private schools can sometimes get away with doing it better. Mostly today, I teach homeschoolers, and they can do what they want to do. They love it. Oh my God, the reviews are phenomenal, and it's wonderful. All differential equations and calculus books are obsolete. Now, George Simmons, Dr. George Simmons, the great teacher, he wrote the best calculus book I've ever seen and the best differential equation book I've ever seen. They're great, but they're obsolete. He wrote them way back then when, they had to use the manual tools. And the problem is you go through one of them and 90% of it is teaching not the concept, the manual tools. Now, I still say those books are great to use to learn the concepts, but then apply Wolfram Alpha to them. Don't bother learning the manual tools. Well, you can if you want to. If you want to learn how to build a horse and buggy and how to fix a horse and buggy and how to drive a horse and buggy, go do it. That's fine with me. Not me. I did, obviously, I had to. But they're all loaded with these manual tools. Now, no STEM professional, they're going to use them anymore. It's just like when the calculator came out, STEM professional engineers, most of them quit using the slide rule. Few didn't, few went ahead and used it, but most of them went to the calculator because nobody liked using the slide rule. It was a pain to use it. It was difficult and error prone. And so a lot of people did. I knew a few that went ahead and were stubborn. There's still people today in this world that drive horse and buggies. There are people that do that. Won't mention any names, but I know a few, and that's okay. Anyway, now, when I teach it, I use what's called spike pedagogy, and I explain that in the book that you can get. Self-pacing, proper content, interactivity, keeping score, and empathy and humor. You make lots of mistakes. That's fine. You're learning. That's progress. It's like a sport. Math is like a sport. And you practice and practice. You make a lot of mistakes. Okay. Anyway, this is the world we live in. And another example would be smartphones compared to landlines. A Wolfram Alpha is like a smartphone, and our standard math curriculum is like a landline. Now, a smartphone's a bad name. It's really a computer, right? My goodness, I take my smartphone and I do so many more things than just make phone calls. And by the way, the phone calls now are cheap. They're free almost, basically. Used to be expensive to make phone calls. Believe me, I know. I used to have a business where I travel all the time. I've been all over the country teaching and working. And it was expensive to call home. And so, 40 cents a minute, 30 cents a minute. Now it's basically free. Okay. So anyway, I give an analogy in this chapter. I'm not going to go through it like I call a hole in a piece of wood. You can read the chapter if you want to. There's lots of analogies you can make up. Just take anything that was manual and hard to do and compare it today to a modern tool. And there's lots of things. Manual calculus and differential equation techniques are obsolete. And by the way, if you get somebody, a math educator, somebody that wants to argue that point, let's have a Zoom discussion on it. I'll be glad to discuss it with anyone. Math, here's the deal. It's no longer a barrier to learning STEM. It's not a barrier. That's why 21st century math programs are vastly superior to 20th century. Now today, there's only one 21st century math program I know about, and that's my 6-tier program. Hopefully that's going to change. Hopefully the other people will come out with even better programs, but they have to use the modern tool. They can't teach the old manual stuff, and they need to use spike pedagogy. Now, what I've done, and the reason I'm doing this for this is for the people that might want to join the STEM Math Club. And this is a video aimed at for everyone that might be interested and want to know. On this, I'm going to have, I have a short video for school leaders so they know what it's about. Then I have another 24-minute video for student parents, and this video is for everyone. And I don't know how long it's going to be. I had a 41-minute one, and this is going to replace it. And this is what you get when you join the STEM Math Club. And notice down here, starting with pre-calculus, you start using Wolfram Alpha up until through trigonometry. That's practical. You can learn all the algebra, geometry, and trigonometry you need for practical math. If you're not going to go to college, you're not interested in science, you're going to be a technical subject, and you want to do good. You can learn all that in a year or less, a semester. I do complex number, and then all this is pre-calculus, differential equation, integral differential equation. This is all done with Wolfram Alpha. Now, just to show you how that is, there's a syllabus, my 6-tier syllabus, and I'm going to start it down at tier 4. You can look at it. And by the way, if you're already a student in a good school, you'll know all the math in the first 3 tiers. You'll know all that. And so that would just be review for you. But in tier 4, that's when you and the teachers are going to start learning some new stuff. And what's going to happen is in algebra, in A5 in tier 4, introduction to Wolfram Alpha. And now I use it from this point forward. First, we just do conic sections. You may have done them already manually. Well, boy, when you do it with Wolfram Alpha, you're going to learn a lot more. I did. I've taught conic sections probably, many times manually over in the past. When I did it with Wolfram Alpha, I learned it better. You can do more examples. One of the things about Wolfram Alpha is you can take a problem that take you 20 minutes manually, if you could do it. And in Wolfram Alpha, it's 1 minute. So you can do them over, you can change a parameter, do them over and over and over. Boom, boom, boom. It's amazing. Functions, graphs, logarithms, all this now is done with Wolfram Alpha. This is tier 4. And now I've done practical trigonometry in the first 2 tiers. Now we're doing trigonometry the way you need it for STEM. By the way, I use George Simmons' book. It's a great book conceptually for the ideas. And so I use his book, but I use Wolfram Alpha. He didn't do that. So you just can't read a George Simmons book by itself. You need to do it along. By the way, every one of these lessons has a tutorial video and a set of notes and a set of exercises. The tutorial video is delivered off of Amazon Web Services, and you're going to be in a learning management system. And then there's notes. This is the set of notes, and you get a PDF of them. If you join the club, you'll get a PDF of the notes. But I also have a printer today that will do them. And I told you this in the 20-minute video, so you know about it. But the bottom line is it's a 500-page PDF because the notes and the exercises, there's a lot in tier 4. It'll take most students at least a year to go through tier 4. Maybe it'll take you 2 years. If you got a really precocious student that works really hard, I've had one student go through it in a semester. But he told me he was working 3 hours a day because he loved it. Well, if you work 3 hours a day on it, I'm not suggesting you should do that. I think an hour a day is plenty for most people. Here's differential calculus. Here's integral calculus, all with Wolfram Alpha. Integral calculus, by the way, this is the one that flunks more kids out of engineering school than anything I know of. Very difficult manually. Wolfram Alpha, boom, go right through it. Easy, easy, easy peasy. And then differential equation. Now these are, and by the way, very few high schools teach integral calculus. They usually teach differential calculus and they stop. And good reason. My goodness, to do differential calculus manually is difficult. It's, whoops, I went all the way to the top. Okay, there's tier 1, how to use a calculator, pre-algebra, 10 lessons, geometry, 19 lessons, practical geometry. Trigonometry is only 7 lessons, practical trig. You get done with that, you'll be able to go out and join the military, go into some kind of apprentice program, whatever. I've got students going through carpenter apprentice program now. Then the math is phenomenal. Tier 3 is getting ready for the SAT. I use Simmons' book again, and I teach the manual tools for these topics because you got to do it for the SAT. You can't use Wolfram Alpha on it. And by the way, once you learn Wolfram Alpha, you can come back and do these with Wolfram Alpha, a lot of them, and it's much easier. But hey, get ready for the SAT, that wonderful test. And now we're back into, like I told you, tier 4. And trigonometry, much deeper now. It's called pre-calc. I told you earlier about complex numbers. In 11 lessons, I'll teach you how you should learn complex numbers for STEM. And this is usually not taught until you get into about it depends on the school, but I've seen it sophomore, junior year, and you need it right away. Special topics if you want to study them, and then differential calculus. Now, differential calculus, isn't that nice how I can't seem to keep differential calculus. The tools aren't too difficult to use, manual tools. They're not, most people can get through differential calculus. You got the Leibniz Rule, for example, very important. Leibniz, he's the guy that invented calculus, right? One of the guys. the Leibniz rule, the chain rule, the quotient rule. And then now manually, here's the point. If I give you a rigged up problem, you can do it manually. Many problems you can't do manually. They don't put them in the calculus books. It's a cheat thing. They know what they can do. So they only put in problems you can do. But if you're an engineer or a scientist and you get a problem, it may not be something you can do manually. Very often it's not. And but Wolfram Alpha does it for you. So this is really a problem you have. This was the course that was well, this course here, this was called Calculus 1. Most kids could get through it. This was the barrier course here, Integral Calculus. It was almost like a initiation. If you could get through this barrier, then you're going to be able to be a pretty, study the rest of the stuff. And I don't know what percentage of kids flunked out of this course, but it was a pretty high percentage, or they just quit. They maybe not flunk out, they just give up and say, I can't do it. I don't want to do it. And then differential equations are the workhorse. Like I told you, you've got to learn differential equations. You can't do science and engineering without differential equations, because that's what you do. You set up a differential equation as a model for whatever you're studying, then you solve it. And that's a function that represents whatever you're doing. Then you analyze that with calculus. Okay, that's the course. And now what happens is, there's no books today to do this. So what we have this STEM math club. And what happens in the STEM math club, when you join it, you're going to get access to all 6 tiers. I just showed them to you, right? The 6 tiers. And everyone comes with it. And so every lesson has a tutorial video, notes and exercises. I started to tell you, this is the notes and exercises for tier 4. It's 500 pages. And it used to be that you had to print them out from a PDF, which you need hard copies of them. But I found a printer that will do them for me very cost effectively. You can buy this 500-page book for, I think it's $17 today. In fact, I can actually sell it to you a little bit cheaper than that if I buy it wholesale. But guess who my printing company is that does this book, where you can go buy it for $17, 500 page, $1,700. Amazon. They have this print on demand thing. It's unbelievable. It's wonderful. And that's, so you can go on Amazon and buy the books for any of the tiers. In fact, tier 1 is only $5.99 because it's not as long a book. You get all these benefits. And this tells you here, you go to STEMmathMadeEasy.org, STEMmathMadeEasy.org. Well, you're probably here because you're watching this video, and you see all the benefits you get. It's what your membership is. And it only costs $50 a year. Now, if you go buy this program, like you want to study it as one of my students, it's $597. Of course, then you have it as long as you want it. You might take you several years to get through it if you're just starting. You're 12 years old and you're starting and you buy it, it may take you 4 or 5 years to get through the whole thing. Depends on how fast you go, self-paced. You're going to get PDFs of all the notes, but you could go to Amazon and buy them if you don't want to print out the PDFs. You're going to get a free copy, a PDF copy of my Golden Rule for STEM Student book. You should read that book. If you're interested in STEM, you got to read that book. And there's a thing called the supercomputer I'm not going to talk about now, but it's a phenomenal tool. It's a phenomenal tool. It costs $300. You're going to get a $100 coupon on it. You'll learn about it later if you join the club. The school can set it up for for nothing. Any school can set this club up. In fact, we give the school 2 free memberships, one for a leader that's a teacher and one for a leader that'll be a student. Could be 2 teachers, 2 students, but usually it's a teacher and a student. They're going to lead the club. You got to have a club leader at your school. And so we give, so they can evaluate it before they start getting other people to join it. So it costs them nothing to set a club up. And then if you join the club, and by the way, if you are interested in STEM, you need to find a club to join. Now, if your school doesn't have one, go to them and ask them to do one. If they won't do it, fine. You contact us and we'll find, there's online clubs you could probably join in. We'll find a club you can join somewhere. Maybe another school in your area has it. By the way, anybody can set up a STEM math club. A church can set one up. So a homeschool co-op group can set one up. Anybody can set one up. All you got to have is a bunch of STEM students, and you need a leader, which will be either a teacher or a coach. And by the way, the teachers love it because all of a sudden now they can work with students and do problems and do projects and all that, and they don't have to worry about, oh my God, I got to teach you all this horrible manual stuff. We got this model tool. Now you got to learn to use it. You can learn on your own, but I'll tell you, it took me probably for some of the topics, it took me 2 or 3 hours to figure out how to ask the right question. And I teach you that, and you learn in 5 minutes. So it's a time saver is what it really is. So that's what this is all about. So as Dr. Dale, I really appreciate your watching this video. If you're interested in STEM, whether you're a teacher or a student, or maybe just a person interested in science and engineering, and you could, any age, you could be 60 years old, or you could be 10 years old. It doesn't matter. You need to start learning this. And ideally joining a club if you can find a club to join. And that's what I recommend you do as quick as you can. And then you'll find this is going to be open sesame to learning STEM math and learning the modern phenomenal tool Wolfram Alpha. And I will also tell you, there's a thing that came out even later called in 2016 called Wolfram Language. And I'll even tell you about that. That's a whole nother story. That's the next stage then. And we're going to start with Wolfram Alpha. Okay, Craig Hain, Dr. Dale, I look forward to seeing you on other videos. I wish you to have a very successful and wonderful life if you pursue any kind of a STEM career.